developed prior to performing the numerical simulation. And then I will show you the results of smart proxy modeling, both in space and time. And by results, I mean reservoir pressure distribution in the entire reservoir and CO2 plume, CO2 saturation distribution throughout the reservoir. So with that, the only thing I wanted to add, if the time was short, prior to showing you how the smart proxy model is developed, I would first show you the results, because if the results are not good, so what difference does it make how the technology is developed, right? So when you see the result and you like it, then you say, now I know, I would like to see how you did it and how it's developed. But given the fact that there is enough time, more than an hour, so I will try to go through the entire process. So first and foremost, let's talk about CCS, carbon capture and storage. Hopefully you all know this in detail, so I'm not going to go into a lot of detail, just provide you some ideas that why we're doing this. So carbon capture is separation and capture of CO2 from the emission of industry prior to it will be released to the atmosphere. And of course, carbon storage is when the CO2 injected in subsurface geological formations. And it usually can be done in depleted oil and gas reservoirs, or it can be done in saline aquifers. And geological formations have the features that it safely stores CO2, since it has safely stored oil and gas for hundreds of millions of years. Therefore, if we put the CO2 in the same place, it would be quite safe to be there for hopefully hundreds of millions of years without, and that's going to help the climate change issue. And carbon storage must be safe and must be permanent, as I mentioned, they would really be, and it must be cost effective. One more item that I'm sure you all are familiar with is the trapping mechanism of CO2. The structure trapping, of course, is when the CO2 fluid migrates vertically as a plume until reaches the top seal of the cap rock. Usually that's the shale. And there's residual trapping, which is the CO2 moves as CO2 moves, then fluid replaces it, but part of it is left behind as unconnected, or what we call in petroleum engineering as a residual. And of course, two more things. One is the solubility trapping. When CO2 dissolves into the salt water or in brine, the brine carrying CO2 becomes denser and will sink to the bottom. And finally, it's the mineral trapping. The final stage of CO2 trapping occurs when CO2 dissolves in water and forms a weak carbonic acid. This weak acid, after a long time, can react with the minerals in the surrounding rock and form solid carbon minerals. So that's very, very simple and very short idea about what happens when you do CO2 injection and storage information. But let's talk about one more thing before we start the CCS analytics, and that is, why do we need to do CO2 storage? So fossil fuel energy that generates CO2, it has been used extensively in the world in a very long time. So as far as the US concerned, in 2020, about 69% of all the energy was oil and gas, from oil and gas, 10% was from coal, 12% was renewable, and 9% was nuclear. So that is in US, but in the world, globally, it's, as you can see, there is not much difference. The oil and gas was about 59% versus 69%. The coal was more, to about 25% versus 10% of US. And renewable is almost exactly the same. And nuclear in US was higher than other places. That was in 2020. So let's look at from 1965 to 2019. That shows you how much globally oil was produced and was actually used. Sorry, not produced. As how much was consumption and this type of energy. And this is how much coal was used, and this is how much natural gas was used. And we put it together literally in these globally in this time that I showed you. About 23%, 24% was natural gas, 44.3% was oil, and about 32% was coal. However, how much historically CO2 was generated by them? Although natural gas was provided or was used, but 25%, it only did 16% of CO2, while coal did 32%. It created 42% of the 41% of the CO2, and for oil is almost the same amount. Couple of more items very quickly at that how in different ways the energy consumption has been done. This is only for 2020, but it's not that different as we go forward. So the petroleum or the oil, that's how it was used. 26% in industry, 68% in transportation, very little in residential, commercial, and electrical power. When you go to natural gas, you can see that it's 39% in electrical power, 33% in industrial, but less in transportation and residual income. When you go to coal, then you see overwhelming majority of that in electrical power, about 9% in industry, and almost none in others. Whereas in renewable energy, but 60% of it was in electrical power and 20% in industrial and so forth. And when we go to nuclear power, it's all in electrical power. And the whole thing I'm going to show to you again in industry, industrial, how much oil, how much natural gas and coal and renewable and nuclear is used. In transportation, overwhelmingly is oil. In residential, there's a lot of natural gas. There is some oil. And when it comes to commercial, natural gas plays a very important role, and electrical power, as you can see, again, natural gas plays an important role. So currently, fossil fuel energy has a certain price. This is, now I'm going to talk about literally why we should do what we're doing, which is CO2 capture and storage. Think about this. Currently, fossil fuel energy has a certain price, right? And it is commonly used by human species throughout the entire world. There is a question, can soon, the word is soon, how soon? Can fossil fuel production be stopped or significantly reduced and be substituted by renewable energy? That is a question that we need to think about. Keep one thing in mind, if this happens soon, there will be a serious difference in the energy price. Why? Because the renewable energy right now in 2020 or in this decade, we've been using it for a couple of decades. It's a good thing, but it doesn't, right now, its price is not the same. This only can be done, this substitution of fossil fuel energy with renewable energy or any other type of energy that brings down the CO2 production. This only can be done once the energy price is not seriously increased. And if you do not believe that, I strongly recommend that do a bit of a research in what recently happened in Middle East, in Asia, and in the United States regarding the energy price. Go and find out. I mean, if you have a question, I'll talk about it for you at the end, but it'd be nice. Go see what happened in November 2019 in the Middle East. And in January of 22, last month, what happened in Asia. and in the United States, what happened in December 2021 when the price went went high. And why am I saying that? And is that because, okay, when you see that, then the question is, does it make sense today and quickly we change the fossil fuel and stop it and bring in other renewable energy that has a lot more higher price? Honestly, that answer is no. The next few decades, while waiting for the renewable energy to be generated in the same amount and be available to all human species at the same price of the fossil fuel that it is now, the only thing that makes sense to be done to address climate change is CO2 capture and storage. So it is all about reality and science rather than politics. With that, let's talk about CCS analytics and see what it is. So currently, at least in the next few decades, I would think about at least 3 decades, the most realistic way to address climate change is through carbon capture and storage. Carbon storage requires petroleum engineering expertise. That's one of the major characteristics that I would like to communicate with you and show you and tell you why petroleum engineering, specifically reservoir engineering, is incredibly important right now in climate change address. And that is through carbon storage that we will be talking about. AI-based carbon capture and storage requires 2 main characteristics. First of them is domain expertise in carbon capture and storage. And why am I saying that? This is something I always believed until I literally started communicating and interacting with those people who are engineers and who are very smart. Don't get me wrong. However, when they want to do carbon capture, the way they think and the way they work is very, very different from reservoir engineers. And that's why the results they get is quite different from what we do. And specifically when it comes to CCS analytics, when they use AI and machine learning to do this, and they're not domain experts in petroleum engineering and reservoir engineering, the results that they get, even when they are good in AI, it's very, very different. This is something that I've been exposed to, and literally that's why I came up with this. So people should learn and should know what they need to do in order to do carbon capture and specifically carbon storage in AI based. So domain expertise is one of the major characteristics of carbon capture and carbon storage. And the other one is strong experience of realistic engineering application of artificial intelligence and machine learning. And that is the key word. This is not something I'm going to go into the detail in this presentation. I do have a whole complete presentation on this topic. And what that topic is what is realistic and what is engineering application of artificial intelligence. Unfortunately, the use of artificial intelligence in oil and gas industry, this is what I was exposed to for a very good long time. And in the past 5 years, when we started using it in other engineering applications, such as mechanical engineering and chemical engineering, I found out what I'm telling you is not only correct in petroleum engineering, but it's also correct in other engineering application. And that is that artificial intelligence used by engineers, it's not used in a realistic fashion, unfortunately. They have a lot of those who build companies and try to make money. They use it in a fashion that has little to do with the true realistic engineering application of AI. To me, right now, the engineering application of AI in the petroleum engineering, unfortunately, is very poor. I have a whole complete presentation on this. If you're interested, I'll go into a lot of detail on that. But right now, I just want to let you know that it is incredibly important to have a realistic understanding and expertise in the engineering application of artificial intelligence and machine learning. So carbon storage can be done both in mature fields and in green fields. When we talk about mature field, carbon storage, sorry, in a mature field is in hydrocarbon production related fields, which some of them could be depleted oil and gas reservoirs. Some could be using CO2 as EOR. And when it is used for saline aquifer, that is a green field. As reservoir engineers, you probably know what the difference is between mature field and the green field. Green field is a new one. Mature field is a brown field that's been produced for a while. There's information about it. So AI-based carbon storage, it's analysis, modeling, uncertainty quantification, optimization, and decision-making, as well as leakage detection of CO2 after the carbon capture. AI-based storage can be done both in mature fields and in green fields. In mature fields, we will be using a technology called AI-based reservoir modeling. It is called top-down modeling. Again, I have a completely different presentation on that if you're interested in. And when it's used for green fields, then what we have to use is not top-down modeling. It's a different application of AI and machine learning. And it is AI-based numerical reservoir simulation, which is called smart proxy modeling. So when it comes to the mature field, the top-down modeling, so TDM, or top-down modeling of CO2 sequestration storage, requires actual field measurements and a reasonable amount. The CO2 sequestration top-down modeling makes absolutely no assumptions. It makes no interpretations. It makes no simplifications. It makes no preconceived notions or biases. It does reservoir modeling in a completely different fashion as we do in numerical reservoir simulation, or what we have been doing in our industry for the past 70 years. This TDM, CO2 sequestration, or CO2 storage using top-down modeling, is all about science, facts, and reality. It doesn't include any interpretation or assumption or biases. However, what I'm talking about today and giving you a case study and some development is the other one, when it's used for greenfield, which is saline aquifer. That is AI-based numerical reservoir simulation. It's called smart proxy modeling. Smart proxy modeling of CO2 storage sequestration requires numerical reservoir simulation of CO2 injection, pressure and saturation distribution of the CO2 plume as in space and time. So CO2 sequestration, SPM, smart proxy modeling, that represents the CO2 storage of numerical reservoir simulation with more than 95% accuracy. I will show it to you. And it can be run on your desktop, not necessarily on HPC with a lot of computer accessibility, but it can be done on your laptop. And hopefully soon it can be done on your smartphone, on your tablet, and it can be done in only a few minutes, whereby the same thing when you do, as probably you have done, that same numerical reservoir simulation of storage, when it has millions of cells, it takes literally almost a whole day, maybe 15 hours on an HPC, which has 20 CPUs. That's the main difference between smart proxy and the numerical simulation. The key is it can done it with very, very high accuracy compared to numerical reservoir simulation, and it can do it so fast. So let's talk about what smart proxy is, smart proxy modeling. First, before we talk about smart proxy modeling, you have to know what proxy modeling is, which I'm sure you do know, but let me very quickly go through it. So give you, so proxy model is a mathematically or statistically defined function that replicates or approximates the response of a full-scale simulation model output for selected input parameters. This is this is just a proxy model. Now that full-scale simulation model, since its development of the full scale of a complex physical phenomenon takes a long time, even on HPC, high performance computing. The objective of the proxy model is to perform numerical simulation in a very short period of time. How does it do that? Currently, there are two types of proxy models. One is what I call traditional proxy models, which have been around for a very, very long time, more than 70 years. And the other one is smart proxy model, which uses AI and machine learning, and that is the newer one. The traditional proxy model generates the proxy model using mathematics and statistics. Generating proxy model smart proxy model uses AI and machine learning. You see, guys, ladies, gentlemen, what does that mean? That means there is a difference between AI and machine learning and mathematical equation and statistics. Remember, I told you there are problems in engineering, specifically petroleum engineering, about AI and machine learning. A lot of people who are domain experts and engineers, unfortunately, they do not realize that AI and machine learning is different from modeling physical phenomenon using mathematics or using statistics. A lot of them think machine learning is a statistics. That is unfortunately a minimal understanding of what AI and machine learning is. Again, that's a different presentation that I can share with you if you're interested. The traditional proxy models are developed using either statistical or mathematical approach. Traditional proxy models were developed more than half a century ago, about 70 years ago, in 1950s. There were two types. The one is reduced order model, ROM. The other one is response surface model, RSM. RSM are used very much in almost every single commercial numerical simulator that you probably use from different companies at the university. We use it here as well. But that is a response surface model. It's application of statistics. And we'll talk about it a little bit, but you can actually do a little bit of research and find out what it is. Explanation of ROM by ANSYS. ANSYS is a company in computational fluid dynamics, but the same is true, of course, with Schlumberger, T Navigators, and everybody who makes numerical resource simulation for us. It's a company that makes a commercial simulator. This is what they're saying, which is very, very correct. They say reduced order model, ROMs, are simplifications of high fidelity complex model. That's absolutely correct. Engineers can use ROM to reduce the time it takes to optimize and study a complex system. This is what this commercial company is saying. Engineers can use ROMs to reduce development cycles, shrink research budget, get to market faster, and limit computational resources. All of these are correct. And again, they are saying it, I'm not saying it. ROM simplifies, this is the key words, folks, it simplifies the mathematics of the numerical reservoir simulation. And a lot of time that simplification is minimization of the number of cells and the time step. That is ROM. And the other one, response surface model, RSM, it's a method that was introduced by George Box and Wilson in 1951. They suggested using a second-degree polynomial model to do it, and they acknowledged that this model is only an approximation. Remember, last one was simplification. This one's an approximation. But they use it because such a model is easy to estimate and apply even when little is known about the process. So why did I tell you? Because if we do not correctly understand what traditional proxy models are, then smart proxy models don't play a big role. But now that we know what those are, smart proxy is a very, very different from traditional modeling, traditional proxy modeling. Smart proxy model is a complete paradigm shift in how to build proxy models of the numerical simulation. The proxy model, this is the keywords, folks. Proxy model includes absolutely no simplification of numerical simulation and no approximation of the numerical simulation. It replicates the results of the original numerical simulation at very high accuracy. I'm going to show it to you. And it does it at the grid block at cell level for every time step. So it doesn't reduce the number of cells. It doesn't reduce the time steps. It doesn't matter how many cells, from hundreds of thousands to tens of millions, and as many time steps that you have. Another thing is the smart proxy model decreases the computational footprint by orders of magnitude. Smart proxy model can have thousands of deployment in a short period of time, and it can have highly complex numerical simulation can be run quickly on desktop, laptop, and hopefully soon on a tablet and a smartphone using smart proxy. This is what smart proxy is. So very quickly, smart proxy, unlike reduced order model, does not simplify the physics of the numerical simulation. Smart proxy model, unlike ROM, does not reduce the numerical simulation resolution in space and time. And when it comes to response surface model, smart proxy, unlike RSM, does not use statistics. That is a very key word, folks. A lot of people think statistics and AI and machine learning are the same thing. They are not. When people tell you that, stop listening to them because you're wasting your time. Does not use statistics. It doesn't use a curve fitting to find correlation between few input variables and some of the output variables, only at a certain time or certain location using hundreds of simulation runs. This is what RSM does. So what is the definition of smart proxy model? Smart proxy model is teaching. Smart proxy model is a process by which you teach. What do you teach? You teach engineering problem solving to what? To open computer algorithm. How? Through data that you get from numerical simulation. This is a very short definition, but literally this is what's happening. I'm going to go into the detail of that. So smart proxy modeling is how you teach engineering using data to open computer algorithm, which is the machine learning. I'm going to define those. Data from numerical simulation that you use for teaching this problem solving to open algorithm. It includes data that is used to build the numerical simulation, as you get it very easily. However, another thing that is required, it's called feature generation. That feature generation explains, that explanation is teaching teachers to machine learning algorithm. That feature generation explains the physics and numerical solution of the numerical simulation. So here's a question. Is it possible to do that if you're not a domain expert in the development of the type of numerical simulation you're dealing with. In this case, we're talking about numerical reservoir simulation. Is it possible for you or for anyone to do this feature generation in order to teach to machine learning algorithm the physics and numerical solutions of the mathematical equations that have been used in numerical reservoir simulation? It's impossible to do that if you're not a domain expert. You will see in a few minutes when I show you the development. So smart proxy modeling lets the numerical simulation easily be used for important characteristics. It does automated history matching of measured data, pressure, saturation, production, uncertainty quantification, CO2 injection optimization, reservoir pressure and CO2 saturation distribution, both in space and time, and CO2 leakage detection. So with that definition, let's talk about proxy model development. Actually, I was thinking to first show you the case study and the results, and then you see it, and if you like it, then you can pay attention to the model development. But since there is time, I'm going to go ahead and show you the development, and then I'll show you the results. So how do you develop proxy model? Development of a smart proxy model is based on AI and machine learning. Question, what is AI? What is machine learning? Recently, I read some definition of these technologies in SPE JPT by somebody who wrote it. And then I was shocked, to be honest with you. Why would people come up with their own definition of this? And that definition is wrong. What you're seeing is the definition of artificial intelligence. I did not make this definition. This is by the people who generated artificial intelligence. Isn't it fair to find what the definition of AI is with those who generate it rather than listen to somebody who has a different idea of what AI is? So what artificial intelligence is the technology that simulates human intelligence. That's why it's called artificial intelligence. It comes from human intelligence. Human intelligence is natural. This one is artificial. So it simulates it. That's exactly what you do with simulation of reservoir, right? So the technology that simulates human intelligence. How? By mimicking human brain. We mimic the human brain in order to analyze, to model, and to do decision making. This is what we do with our brain, and that's why AI is. What is machine learning? Machine learning makes AI possible through algorithms. What kind of algorithm is? It's the science of making computers to act without being explicitly programmed. What do I mean by that, folks? If you know, which I'm sure you do, you know what numerical simulation is, right? So the computer programming that you do, or anybody does for numerical simulation, reservoir computer product, any other kind of numerical reservoirs, numerical simulation, what is it? It's completely explicit programming, meaning what? Meaning that we tell the computer what to do step by step. There is not a single thing that computer does on its own. It only does what we tell it to do. The only thing is it does it fast. That is not machine learning. The science of making computers, what machine learning is the science of making computers to act without being explicitly programmed through using open computer algorithms. What is open computer algorithm? An open computer algorithm is an algorithm that applies to so many different things. It does the same thing. You don't tell them explicitly what to do. You have an algorithm, you just provide the data and it learns from it. The open computer algorithm uses the data from any type of outcome that data was generated from, and then it comes up and it learns from it. That's why it's called learning. Machine learns. Machine is computer. What it do? Machine learning is when you use the data So machine can learn, computer can learn from data. Is it possible, or is it the same way of learning if there is no teaching? Why are you in the university? Because you want to be taught, right? Teaching, your learning at the university comes from teaching, doesn't it? Then why do you think it's different when it goes to computers? It's really not. With that definition, some of the machine learning algorithm that we use in smart proxy modeling is artificial neural network, fuzzy set theory, and genetic algorithm. What are these? Well, artificial neural network, remember that AI and machine learning is mimicking life and the nature as we explained it. Artificial neural network mimics human brain information processing. However, fuzzy set theory mimics human brain's logic. Genetic algorithm mimics optimization through natural selection. Very quick, I'm going to give you one short definition of each one of them. As we know that we said in general for all of them, artificial intelligence mimics nature to solve complex and dynamic problems. Human brain is constructed by evolution to deal with uncertainties and various possibilities. So artificial neural networks, folks, mimics the neurons in human brain for the learning process. Learning through pattern recognition by using data to train a series of open computer algorithms. That is artificial neural network. For fuzzy set theory, it mimics human logic, not human neurons. Fuzzy logic avoids the limitation of two-valued logic, Aristotelian logic. Okay, that's the difference between the statistics. In order to expand the potential to learn and make reasonable decisions based on non-exact information. Human brain does not make decision based on yes, no, black, white, 0, 1, up, down, two-valued logic. Human brain does, your brain, just think about it. It never works like that. So fuzzy set theory tries to follow that process. Finally, genetic algorithm mimics Darwinian evolution theory for optimization purposes. Genetic algorithm is an evolutionary computing process that finds a solution and performs optimization of complex problems through natural selection. Natural selection is how Darwinian evolution theory was done and how you and I became Homo sapien. So with that, smart proxy model development for numerical reservoir simulation. So this is, we have done the same thing for computational fluid dynamics for mechanical and chemical engineers. There are a lot of paper and things like that. If you're interested, I'll show it to you. There could be a different presentation. But anyways, this one has to do with numerical reservoir simulation. Reservoir simulation, you need domain expertise. You must be a reservoir engineer and a reservoir modeler. If you have no idea what reservoir engineering is or reservoir modeling is, then there's going to be a big problem for you to be able to use AI and machine learning to do proxy modeling, smart proxy. It requires domain expertise in engineering application of AI and machine learning. That is another problem, as I mentioned, we have in our industry. So before that, let me quickly go, in case I know many of you know what numerical simulation, reservoir simulation is, numerical solution is, but just to make sure that we're all on the same thing, let me quickly tell you very simple what numerical solution is. Modeling complex physical phenomena requires complex mathematical equation. Many of these complex nonlinear mathematical equations must be solved using numerical solutions because they cannot be solved with analytical solutions with exact answers. It's complex nonlinear mathematical equations are linearized by numerical solutions through minimizing the space and time, and linear solutions of several millions of cells or grid blocks are then added together, and they're communicated with each other, with one another, to generate comprehensive solution. And for us, this is diffusivity equation, which is fluid flow in porous media. It's a complex physical phenomenon, fluid flow in porous media. It's complex mathematical equations, diffusivity equations. And of course, it's a complex, it's a parabolic, nonlinear partial differential equation, as you can see it. I'm sure you know. So in numerical reservoir simulation, let's say this is a field. This is actually a field in Southeast Asia. As we know that that reservoir is heterogeneous and it's nonlinear. It's heterogeneous in static information and it's nonlinear in dynamic parameters that it has. So what do we do? To do numerical simulation, we put a Cartesian series of grids on it, and then we go to one of that grid points. And if you see, that little grid is right here. This is no longer heterogeneous and nonlinear because it's small in the space, so it becomes homogeneous in a cell static parameter. So in a cell, static parameters are homogeneous, and in a cell, dynamic parameters becomes linear. Why? Because the time step's small, and you see the cells are small. That's why we have to go. So this is another cell, this is another cell, and as you can see, this is as you very well know, this is what we do. Correct? Now, Smart proxy model is developed using the data that is incorporated in the numerical reservoir simulation. That is very simple because you know as what data is there. However, it also do feature generation. Features that are generated by domain experts to help teaching numerical reservoir simulation to the machine learning algorithm. I give you some examples, not all details, because this is not something, I mean, we teach courses on this, but let me go ahead and give you some ideas. So the data that is incorporated in the numerical reservoir simulation is our reservoir characteristics, well locations, production and injection characteristics, and everything that you put in the numerical reservoir simulator, right? How about feature generation? So features that are generated by domain experts to help teaching the numerical reservoir simulation in the machine learning algorithm are things such as numerical reservoir simulation is cell-based, isn't it? How can we share that? How each of the several millions of cells are handled by numerical reservoir simulator? How pressure and saturation in each cell is modified as a function of space and time. These, you have to generate features as data to communicate that with the machine learning algorithm so it can, you teach it so it can learn. An example. Unlike traditional statistics, folks, that requires hundreds of numerical simulation runs to generate proxy model, AI-based proxy model, which is smart proxy model, only requires much less numerical simulation run, 10, 20, no more than 30. In statistics, you need hundreds, 250 up to 500. So let me give you an example. Let's assume this is a numerical simulation. In this case, you can see that the blocks that you have are not in cubic, right? Does it work? Absolutely the same. And if it's in cubic parameters, these cells, they're not exactly the same size. Does it work? Absolutely yes. But let's simplify it. If your cells or grid blocks in the cube in that fashion, how do you deal with it? How do you teach what's happening in that to the machine learning algorithm? Question, how these cells communicate with each other? How does things change in that grid block? Well, it changes by what happens to the cell next to it. These are the cells that the one in the center. So this cell, we call this, let's say, if you have 100 million cells, every cell has to be dealt with one at a time. So every cell, we take one of them, we say, okay, this cell, like everything I'm saying about this one cell applies to all of them. We say this cell is, we call it the focal cell. Then it communicates through the entire plane with how many cells? 6 cells. This 6 cells, whatever happened, I call it tier 1 cells. These tier 1 cells are the cells that communicate with my focal cell through the plane. Everything that happens in my focal cell is a function of what happens to these tier 1 cells that communicate with the focal cell through the plane. How it works, right? How the plane, the communication between these two works, right? We call this tier 1 offset cells. Focal cell is every single cell that we do this for. However, there are cells that we call it tier 2. This tier 2 cell communicate with focal cell not through a plane, but through a line. However, when they do it through the line, in the numerical simulation, they don't do that directly. Rather, they do that in 2-step. It goes from tier 2 to tier 1, and then from tier 1 to focal cell. How about cells? These are we call tier 3 cells. These are offset cells that communicate with my focal cell through a point. Well, how does it happen through a point? Well, it never happens directly through a point. It goes from tier 3 to tier 2 to tier 1. Correct? It goes from point to line, from line to plane, and plane to the focal cell. With that, you have plane communications in 1 step. You have line communication in 2 steps, and you have point communication in 3 steps. Okay, so this is called plane communication, this is called line communication, and this is called point communication. This is called tier 1, tier 2, and tier 3. So you let the machine learning knows what is happening here. So let's do it in 2Ds to make it easier to show, but literally we'll do it in 3D in the numerical simulation and in the smart proxy model. Every single cell that exists will be a focal cell that you generate the data for. You say, okay, if that is the focal cell, folks, then I have neighboring cells. These neighboring cells communicate with it in 1 step. These neighboring cells communicate in 2 steps. Stop. A focal cell has distances to the boundaries, right? So every focal cell has different distances to all the boundaries that exist in the numerical simulation. This focal cell is in a numerical simulation that includes maybe production wells, and you have to identify its distances from those production wells. And they may be injection wells, then you have to identify its distances from the injection wells. However, another thing that we can say, these are the features that you have to communicate with the machine learning and teach it, right? Another step, let's assume this is again in a 2D, but again, we do it in 3D, not 2D, but 2D easier to show. If a cell, like the one is shown here in the black. If this is the well, what that well could be an injector or the producer that exists here, and you have to identify its completion in which wells. But the thing is, there is a distance to the same cell in the same layer that where the cell is injecting or producing. However, there is permeability in X, Y, and Z direction. Therefore, what's going to happen in the cell above and the cell below also impacts it. Therefore, we have to provide those distances as well. Another focal cell, and this is the injector or producer well. And these are the 3 cells that I showed you, the distances, that is important, that's telling, because their production of these 3 cells impact much more than anything else, any other cells in the focal cell, injection of these cells. So another thing that's important are these cells. The reservoir characteristics these cells identifies not only the distance, but the amount and the way communication of injection on production handled from this well to this cell. You see, all of these, because if you know how the numerical reservoir simulation is built and works, then you have to use all these details that I mentioned and generate new features for all of that and communicate that with the machine learning algorithm. So fuzzy set theory can help smart proxy model development through key performance indication of large number of potential input parameters. It can categorize the cells in the numerical reservoir simulation that might enhance and speed smart proxy model. Artificial neural network can help smart proxy model development through cell-based training, calibration, validation of the AI-based model. And why do I say that, folks? A lot of people in our industry, and even right now, I started this many long time ago, almost 3 decades ago. I did this smart proxy. Actually, I did it in 2004. But anyways, my point is, at that point, we built our own software from A to Z for everything. Now, there is no reason for that. Why? Because you have scikit-learn, you have different libraries, the TensorFlow and so forth that you can use, right? However, keep one thing in mind. Nobody has developed these for engineering application. They're developed for non-engineering application. And don't get me wrong, I'm not saying non-engineering application or general artificial intelligence is easy. No, actually, sometimes it's much tougher than engineering application, but there is a difference between them. They're not the same thing. Therefore, if you use the same algorithm that you use for non-engineering application, you have to make some changes. They do not use training, calibration, and validation. They use only training and testing. Literally is training and calibration. And there is no validation. There's only, it automatically divides the data in 2 parts. We divide it in 4 parts. I will explain it to you. But when you use that, you should, you make sure you have to make these changes to it. So training, calibration, and validation, that's 3. The 4th one is blind validation. So that you take the entire data set that you're dealing with, you divide it in 4 categories, not only 2, because it's required for engineering. That's another whole different thing that we can lecture on. Performing the smart proxy model on numerical reservoir simulation runs that have not been used during the development of the smart proxy model. So blind validation are numerical reservoir simulation runs and geological realization, as you will see, that were never used to build to smart proxy model. Why do you do that? Because when you build a smart proxy model, your numerical reservoir simulation runs are going to be all new ones. So the question is, does the new numerical reservoir simulation work? And your smart proxy does good. It does very good in training. Calibration and validation is blind, but not as good as training. But blind validation is the worst case scenario. If it doesn't do very well in blind validation, then your smart proxy is not correct. I'm going to show you the results in blind validation today only, by the way. So genetic algorithm can help develop smart proxy model through uncertainty quantification, optimization of CO2 injection, and contribute to any potential decision-making process. So now that it's covered, it took 1 hour to cover that. Now let me show you a case study, and hopefully I can finish that in 20 minutes or short. This has been done as CO2 storage sequestration in a saline aquifer. So the CO2 storage in saline aquifer through numerical reservoir simulation. The reservoir simulation is heterogeneous reservoir characteristics, the various layers thickness. So as you can see, not all the grid blocks have the same size. They change, as I showed you. Layers are not flat. They go up and down, and grid blocks are not the same size. Grid blocks are changing. The layers of thickness are different. And this is the same. This is the model that was developed. This is the model you just rotated a bit. So the saline aquifer is in sand. What you see here is in gray, and it has some cap rocks, which are shale, and you can see it in yellow. So as you can see here, the CO2 storage in this numerical simulation includes 4 injection wells, as you can see here. And the number of cells is 125 grid block in x-axis, 125 in y-axis, and 65 layers. And when you multiply them together, you have more than 1 million grid blocks. So some of the reservoir data are taken from Citronelle field. Citronelle is a saline reservoir located in Mobile County in Alabama in the United States. That's where we got the data to build this reservoir. And the way we did actually, it's 65 layers, and as you can see, there are 24 layers. 4 layers on top is shale, 6 layers in the bottom, middle of the shale, 4 layers in the bottom is shale. But the sand where the injection takes place and storage takes place is 24 layers on first part, and then 27 layers in the second part. Together will become about 51. And of course, as you can see, these are shale, and the rest, at least 51, are sand. And these are the actual porosity permeability data that was received from Citronelle. And we identified in 5 different rock types, but we used these 4 different rock types, 1, 2, 3, and 4, based on what you see here, and used it in this numerical simulation. We called this one very conductive, we call this conductive, we got this one tight, and we got this one very tight. So actually, this is how we did it. As you know, there are 3 shells, and the 24 on the top, 12 were rock type 4, which you see here, 12 in the mid C3 here, that's a rock type 3, and on the bottom, we got 14 in C2, 13 in C1 rock type 1. How about injectors? As you say, there's 4 injectors in the reservoir, and the injectors wells are completed in all 51 sand layers. The injector wells will be operating using 2 constraints. The constraint is bottom hole pressure. We make sure the bottom hole pressure is below fracking, and the maximum injection rate based on what we have. So as you can see, we made 20 simulation wells, and each injection well, so we have 4 injection wells in each simulation well. So each injection well has different injection rates as far as BHP and is concerned, and amount of simulation run. So what you're looking at, this is this injection well. Since we have 20 simulation run, you have 20 injection rate and 20 BHP. Each one of them represents one of the simulation run. This is for this well. These are the 20 for this well injectors. This is 20 for this injector, and this is for 20 another. As you can see, each one of them are completely different. It was not exactly the same. So these are the 4 injectors. As you can see, the 20 injections and 20 BHP for wells in 20 simulation run that was made. And the simulation run made for 300 years. The numerical simulation. In that 300 years, what we did was 30 years. Actually, this was a project we did for the U.S. Department of Energy. That's what they requested, actually, what we did. So from 2020 to 2320, the 300 years, out of this 300 years, for 30 years, there were injection. CO2 was injected for 30 years, and then after that, the injection stopped, and we looked at post-injection for 270 years. And of course, you have distribution of pressure in each layer. You have distribution of CO2 saturation plume in each layer. And of course, you can see it in cross-section as well. So with that information, and one more thing I need to share with you before I show you the results is the geological realization. We were asked to generate 20 different geological realization for those 20 different simulation runs that have different injection. So these 20 geological realization were generated to be used as geological models for numerical reservoir simulators. Each geological realization has different porosity and permeability distribution. And the sequence of the rock types along the reservoir layer and the relative permeability is the same in all the geological layers. So here I'm going to give you an example of one of the, if this is the reservoir model, this is the layer 5, right? If you go to the layer 5, you can see in geological realization number 1, number 4, number 19, and number 20 in layer 5, and you can see how the lower porosity and the higher porosity or permeability is changing. And this is for layer 10. You can see the changes that takes place. This is the layer 37. We go in the bottom, as you can see for that layer, the different realizations provides different distribution of porosity and permeability. And this is layer 50, way in the down. So in the total, we have 20, this is porosity map of 20 geological realization for each one of them. This is for layer 5. However, as you can see, run 5, run 9, 13, and 17. These 4, we use it blind validation. In other words, out of the 20, we build the model, smart proxy model, only on 16. We do not do any information, provide any information of these 4 blind validation to the reservoir smart proxy model development. We only use the 16 smart proxy, 16 numerical reservoir simulation. Each one of them run once, 16 simulation runs of 16 different geological realization, build the smart proxy, we train, calibrate, and validate, and then the best result have to be shown on the results of the blind validations that never used to build the model. Okay, so literally in this context, you can generate more reservoir simulation models and you still get good results. That's what it tells you. This is layer 5. This is layer 10. You see the differences, and this is the 4 that are blind. And this is layer 15. This is the 4 that are blind. And this is layer 20. Again, you can see the blind. This is layer 37. I'm just giving you a lot of examples. This is layer 50, and you can see the blind. And this is the distribution of porosity as a for several of the simulations that you can see how porosity is different from each geological realization. When you see it in things, we see it in gray. This is the permeability distribution of different rock type. This is rock type 4, 3, 2, 1, as I showed you. And of course, this is the pressure distribution when this is the results that we get. You can see how different they are. This is what we are trying to model. And this is the saturation we're trying to model. You can see how different they are in different reservoir simulations. So with that, let me show you results of the smart proxy model in space and in time, both. So results of smart proxy model. So smart proxy model, it's we're using fuzzy pattern recognition, of course, and fuzzy logic and artificial intelligence. One of the important to note is the fact is that fluid flow in porous media, you all know, is a function of space and time. So do not use, a lot of people use LSTM, long short-term memory. in order to build it. And when they do that, they could get good result on a single well, of course. But what they don't understand is they're avoiding space and they're doing it only on time. And that's not going to work. Okay. Another thing that people do, they use a picture. They try to do convolutional neural network to develop picture training, that's why I'm saying people have very little understanding of AI and machine learning in engineering application. Anyways, so with that, let me show you the next several slides. We compare the reservoir pressure and reservoir saturation, CO2 plume, its distribution both in space for every single cell in every single layer and in time, generated by commercial. We use CMG, the commercial numerical reservoir simulation was generated, and with smart proxy. So we show you two things. One, what a CMG does and what smart proxy does. Compare them together. The main comparison is not with geological realization and numerical reservoir simulation that were used in developed smart proxy model. What does that mean? I'm going to show you the result mainly on blind validation. Those remember I said run number 5, run number 9, run number 13, and run number 17 that we removed, we did not use to build the model. Okay, so remember, these are the 20 simulation runs, 20 geological realizations I showed you. Out of these 4 are data used for smart proxy blind validation. The blue ones are data used to build the model. So these green one was not used in any shape or form to build the model. Never seen it. Smart proxy model development it includes training, 80% of this blue data, calibration, 10% of the blue data, and validation, 10% of the blue data. That's all 100%. However, the green one, the blind validation, they are not used during model development. Keep that in mind. So here's what we do. We train, we calibrate, we validate, and when we're done, we perform line validation. So artificial neural networks foresee pressure and CO2 distribution. We use all the information that we generate, data, and we first do pressure, then we use the pressure, add it to more data, and we do saturation. So with all that, this is the end of it. I'm going to show you first the reservoir pressure distribution of smart proxy in space and time. Okay, so I'm going to show you, I'm going to spend a little time on this one, but then I'm going to show you many of these so you can see it's important. So what you see is a blind run. This one is blind run number 5. We have 4 blind run, number 5, number 9, 13, and 17. And each one has 51 layers. So when I go through time, I have to show you 1 layer at a time. Or I can give you one time and go through all the layers, right? So in this case, I'm going through layer 5, and I'm going through from 2020 all the way to 2026. You see 3 plots. Here, this is what the CMG generated. This is what our smart proxy generated. This is the error between the two. The maximum is 5%. So it's from 1 to 5%. So you see any color that goes here goes up to 5%. All right. So this, as you can see, is almost less than 1% error for 2021 in run 5 of layer 5. So the next one is 2022, 2024. So I'm going to go back again so you can see quickly how this is run 5, layer 5. Next one, the run 5, another layer, 21 for different times. Ready? Sorry, again, to layer 21. Sorry. So 2025, 4, 3, 2, 1, 2, 3, 4, 1, 5, 6. You can see that's layer. Next is layer 23. 2, 3, 4, 5, 6. Forwards again, forward. You can see the difference between them. I'm going to show you one of the blind validation. This one is geological realization of run number 13. And we're going to go to layer 26. In that layer 26, I'm going to show you from February 2020 to December 2022. There, I showed you on an annual basis. Now I'm showing you on a monthly basis. So what you're looking at here, this is the CMG on the left. In the middle is smart proxy. This is the error. Again, 5% is maximum. And here is every single month that it goes through. Ready? Let's go. I'm going to go and come back to see you twice. Okay, I'm going to go back. So go to the next one. This is going to go to the end, and I'm going to go to the next one. Okay, this one is realization number 5, run number 5, another layer, layer 8. Again, it's going to go monthly from February to December, February 2020 to December 2022. And again, it tells you the month here. This is CMG, this is smart proxy. See the difference. Okay, this one is reservoir pressure distribution for the entire field in one time step. Here, what we do, I showed you layers, one layer at so many different times. Next, I'm going to show you one time at all the layers. So when I do that, then at a third time, I show you a 3D. Because again, this was not done based on picture. This was not done based on layers. This was done based on cells. So we can do it. It's true for all of us. What you see, this is blind run number 5, time step 2020, and you can see this video is going through every single layer from top to the bottom. It's went through the whole thing. Next one goes to another run for another time. This is run number 5, same time. It's going to go through the whole layers. You can see the number of layers up here. Next one is line 13 for a one-time step. Every single layer. One is run number 17 in a time. These are all blind simulators that never been used to build the smart proxy. But it shows you how good you can. All you have to provide is geological realization, and then you send it to the numerical reservoir smart model, smart proxy model, and it provides you exactly the same that your numerical reservoir simulation is with very, very high accuracy. The only thing, it generates it so fast. So space and time. Now I'm going to show you the same thing. This is in 3D. I'm looking from the top. This is blind run number 5, pressure distribution. And you can see it's going to go through the time. CMG, smart proxy error. I'm going to show you exactly the same thing. Now we're looking at 3D from top. Now let's look at 3D from bottom. Same thing. As you see, time goes on and it changes, 3-dimensional. Some people take pictures, do convolutional neural network. We don't do that. For every single cell, we build that. We literally do a engineering application, not a picture application. This is run number 13, pressure from top, looking at it. Same thing, looking at the same thing from bottom. Okay, so what happened? Literally, when we had 30 years of injection and 270 years of post-injection, these were the error. So literally, the monthly, we developed this part in monthly production, this 2 years. And the overwhelming majority of the error was a bit more than 2%. In one case, we had about 5%. Then we went to this area here and here. And you can see in this area during injection and post-injection, we did this in annual steps. And the maximum was 10% error. Average was about 7% error. Then we went to this part. We did it on a decade wise, this area, and we got it average error of about 8%. And then we did this part in every 50 years. And the average was about, for pressure, was about 2%. That was the pressure, as you saw. Now let me show you a CO2 plume distribution space and time. This is CO2 saturation. This is normal visualization. Another, what means that the difference is literally between every single percentage of difference. This is the CMG. This is a smart proxy. This is the difference up to 10% error. And what you're looking at is January 2023, and it's a blind validation. This is generalization number 5 and layer number 6 right now. And now we're going through from 2023 to 2050, from here to here. Okay, so look at it. I'm going to go one by one. So you can see on a monthly basis. I'm sorry, yearly basis, 23, 24, 25, and so forth. This one is layer 7, and it goes from 2051 to 2070. Now it goes from this area. That last one was here, this one was here. Now look at what happens. This one is January 23 to 29th, and it goes yearly basis from here to here. This is another layer, layer 9. Again, blind validation. This goes from 51 to 70, this area. Blind validation, layer realization, layer 14. Okay, with that, let's go to saturation categorization. One of the projects we're working on, national laboratories of the DOE said, don't do it on every value, do it only less than 10% saturation, more than 10% saturation, only 2 values. And in that fashion, the same thing that you saw in layer 6, this is the January of, this is what you get. There's a little bit of a difference. Of course, now I'm going to show you in a dynamic CO2 in 3-dimensional, okay, the same thing. So what you're looking at is blind validation number 5 in a 3D space. You're looking from top. This is plume, CMG, and this is smart proxy. This is error. In 10%, less than, more than 10%. Same thing, looking from the bottom. We'll go to another blind run, 13, same thing, looking from top, 3D. And looking from bottom, the same thing. And of course, this is the errors of this, as I showed you before. So literally, I'm going to end the presentation. Thank you very much. If you have any question, I'll be happy to answer.
Okay, thank you very much for the very excellent presentation, Professor Mohage. It's very interesting that we know about the CCS, what is CCS about, and why we need CCS, and also for the development from the traditional proxy modeling that you explained very clearly up to development of the smart proxy modeling, and we can also see the results, very interesting results that we can see that it's really matched with the commercial reservoir simulations. Maybe for the first time is a big applause for Professor Samo Hagi first. Yeah. As you can see that actually we have in here, we also come from associate professor from NTNU with Askan Jahanbani that also watched this directly in P1.
Thank you. Thank you very much.
So we actually have start from the sessions of the questions and answers sessions. As we can see that there is quite a lot of questions in the chat. And I think it's fair that we can say that we open for the 3 questions first, with 2 questions from the chats and 1 question directly from here. Is it okay? Then maybe we can start from the first questions that starts from there, Mr. Korus. Thanks for the very interesting presentations. Although using proxy models is quick to evaluate the thousands of possible solutions, defining different assumptions and approximations that are not consistent with the physical rules of fluid flow in its specific reservoir may reduce the accuracy of the production or injection forecast. Can you please address how this issue is? Thank you.
Sure. So let me understand the question. Says, although using proxy model is quick, defining different assumptions. Okay, that is very true. This has nothing to do with proxy model. This has to do with numerical reservoir simulation. And because proxy model represents numerical reservoir simulation, then yes, you are correct. There is assumptions, there are approximations, and there is not much you can do about that. That is, if you remember at the beginning, I mentioned that CCS analytics, which is application of AI and machine learning to carbon capture and storage, has 2 parts. 1, mature fields, 1, green fields. With green fields, when you don't have any data or you have very limited amount of data, this is true with oil and gas industry as well. You don't have any options but to do numerical reservoir simulation and move and go forward. And that's why what I showed you, smart proxy can do. However, if you do have some data, and that's another project that we will be working on soon, hopefully, is that when you do have some data, then you do not use numerical simulation and you do not use a smart proxy model. There is another application of AI and machine learning in numerical reservoir simulation, in reservoir simulation modeling, not numerical. It's called top-down modeling. And if you're interested, I have a completely different, I actually teach 2 courses on that at the graduate level, and we've been having it for more than a decade. That is a completely different story. That is building a simulation and a model of the reservoir engineering, a reservoir model purely based on facts and measurement, no assumption, no approximation, no simplification, nothing, no equations. So that has to do with what you're dealing with. If you're dealing with a green field, it's very, very hard to do that. There you don't have any data. So what you're going to do, then the data comes from numerical simulation. I hope that answers your question. If it doesn't, maybe I misunderstood, then you can ask me more.
Thank you very much for the explanation, Professor. Maybe it's addressing. If no, then you can still raise your hand and ask your questions, and we can also unmute you directly. Okay. Okay, for the second questions, I guess it's directly from this live sessions that people come here. Maybe who want to ask maybe some questions.
Sure.
Yep. Okay. Just Professor ask and want to ask some questions.
Hello, Professor Mohaqqaq.
Hello,
This is
sir.
Ashkan. Good to see you again. Thank you for the presentation. Okay, yeah. I actually have the honor to have Professor Mohaqqaq as one of my partners in my future projects. So it is a very important topic for Norway. We have seen large scale demonstration projects in Norway. And recently, the Petroleum Directorate actually opened 2 new areas in the North Sea for CO2 storage, and 5 companies, including Equinor, have applied for the licenses. And the results will be out, I guess, in March. So you're actually helping to the realization of this technology, CCS, and in general, the digitalization with all the use of the AI machine learning you're discussing in petroleum engineering. So thank you for that. And just, I don't have a question, but just a comment based on your previous discussion. So this is actually the problem in CO2 storage modeling. We don't have much data. So we cannot do the TDM. As you mentioned, there is no assumption, and it's based on the fact that data never lies. But unfortunately, so that's kind of a green field. So we don't have much data on that. So it's important to build accurate proxy models. In a proposal that we sent recently, because last year I had an idea to somehow alternate between TDM and SPM for CO2 storage modeling. But the feedback I got was that you don't have much data. So this year I focused more on SPM. And as you mentioned here, the errors can be very small. So in some of our previous works, we got errors up to 5%. And in the new project, so we hope we can get like what you got here, 1% or 2% error. So it's important to focus on this SPM as you did in this, mostly in this talk. This is very relevant for CCS modeling. So thank you very much.
Thank you very much. Much appreciated. Hopefully, we will. One of the things, as you mentioned, Professor, is that once you build a good numerical reservoir simulation and your smart proxy allows you to literally run it hundreds and thousands of times and do uncertainty quantification that identifies if the if the geological modeling that was built is not correct and it's wrong, what could possibly happen? This is what we've been doing in Greenfield for a long time, and of course, what another thing is, you can start with a green field and build it and continuously model it and find out about it. And when it happens, the data is generated. You can literally move it from smart proxy to TDM on a literally monthly and yearly basis until you get it completely from one to the other. But great point. Thank you for mentioning it. I'm not listening. I'm not hearing anything right now. Sorry. Can you guys hear me?
Hello, can you still hear me?
Yes, now I can hear you.
Okay, so it's maybe kind of the sound is kind of small now. Is it, or is it still the same?
Yeah, I can hear you. Sorry, go ahead and ask any question.
Okay, yeah. So for the we have a mic problem here. So for the second questions, we are also coming back for the chats, and we can see that from Muhammad Faiz Bakar is asking about the. This may sound a bit naive, but injection of CO2 may take in the form of supercritical conditions. Will this affect the overall simulation for injection and CO2 plumb migrations prediction instead of using CO2 in gas conditions?
That's quite possible, yes, for it to happen. However, from what we were talking about, however you make the numerical simulation, so what you're mentioning, exactly if that happened, and all you have to do is to deal with the numerical simulation to make sure that it take into account all the detailed characteristics that you believe it's going to happen, and then identify what would be the results of that, and you can simulate that. However, no matter what you do with numerical reservoir simulation, smart proxy still works because it uses exactly whatever you do in numerical simulation, nothing beyond that. We have done that, as I mentioned, we have done that for mechanical engineering, for chemical engineering, in fluid flow, in computational fluid dynamics, CFD, which is we were able to get exactly as good as results that you saw here. We have done it for US Department of Energy on those. So as long, whatever numerical simulation you make, then you can do the smart proxy quite well.
Yep. Okay, I hope that's answer to Mr. Faiz. If it's answered, you can. Okay, I've already answered it. Okay, because it's very enthusiasm, and there's a lot of people that enthusiast to ask questions in here. We open the second sessions about the Q&A for the 3 more questions. Again, 2 from the chat and also 1 directly from here. So we can see the next questions is that okay, so there's quite a same questions, but it's quite a different little bit. The first one is asking about whether it's in the supercritical, and there is questions about you want not to use LSTM, long short memory, or a CNN for the smart proxy models. What architecture does the model use, and how many inputs does this model take in totals?
Yes, of course. LSTM, which is long short-term memory, and CNN, which is convolutional neural network. Those two are good technologies, and I strongly recommend that you learn it. However, what I strongly recommend is do not use that in petroleum engineering, because what you learn from that is how to use artificial intelligence and machine learning to solve specific types of problem. What do they do in order to solve it? However, do not use the same thing to solve it. Why? Because LSTM has to do, only takes either space or time. It doesn't do both of them, but that's why it doesn't work. Unless LSTM only does good thing for decline curve analysis. And you all know that decline curve analysis is incredibly simple. You don't even really need a bachelor's degree to do decline curve analysis. So if you want to do LSTM for decline curve analysis, you're most welcome. But why would you want to? The question is, are you going to add 2 + 2 = 4? You're going to use the AI to do that, or can you do that? So that's the key. If it's very simple, there's no reason to use AI to do it. CNN, or convolutional neural network, is image recognition. When you have a 250 by 250 pixel, which is 6,250 input, if you put only the pixel and do try to find what happens, that's very different from what CNN does. What CNN does, it does a completely different story. If you have 15 layers, 10 of them identifies the lines and the circles, and then in the past 5 they put them together. That's you convolve, you identify different things, and then you convolve them together. And again, we are in petroleum engineering, in reservoir engineering. Question: when was the last time you did picture recognition, image recognition? You didn't, right? You did fluid flow through porous media. So why now picture? Because somebody in Google did picture recognition, then we have to do the same thing because it worked for cat and dog. So that's what I mean. Do you have to learn? Yes, learn what it is, but don't use the same thing. Figure out how they solved it, and you have to do the same thing and come with a different solution for what you're doing. So the next question is, how many input does this model take in total? Well, okay, to be very honest, you can start and generate 1,000 input. However, it is not a good idea to use all the 1,000 input. One of the things that we do, we use fuzzy pattern recognition in order to find out. Prior to building the model, we call it KPI, key performance indicators. We identify and we try to put a distribution of importance of every parameter of the 1,000. And then that doesn't mean we believe exactly the same thing happening, but if you want to find the 20, we take the top 20 to build the model, and then go another 20 below that, and back and forth to find out what makes best sense. And the thing that happens is the data has become important. The hyperparameters of the modeling becomes also important, but after the data provides you with a good results. So it's a process through which you have to, it takes experience. It takes a lot of work that you have to do and get better and better and better. It's not something that if you do once or twice, or you understand the mathematics behind it, then you're done with it. That really doesn't work, but just keep doing it long as far as you're an enthusiast on the technology, keep doing it and do research, do work, and eventually you become very, very good at it. There's no doubt about that. I hope that answers your question.
Okay, Professor, thank you very much for the on-site explaining. It's very clear for the inputs and also what the architecture that we should use for developing the smart proxy models. And in here, I will open one questions directly in live sessions.
Sure, I will take any question.
Okay, there is no question. Let me again, on behalf of a student at NTNU, appreciate you, Professor, for the time and energy you put today.
Sure.
I have a request. The other time that I had chance to attend in a webinar that you were presenter, you shared a document where you had gathered some access link to the materials for getting familiar with machine learning and video lectures. I want to, with your permission, share this document with people who are interested.
Absolutely.
Thank you very much. And the last request, although you are not here, we're gonna to have a picture with you. So if it's okay with you, we have you in background and we take a picture while the students come here.
Wonderful.
Thank you.
Send me that picture, please.
Yeah, absolutely. Please follow us for a picture here. Can you share the picture?
Yeah. Okay. Thank you very much for the photo sessions and also for interesting presentations, interesting question and answer. I see that there is still a lot of questions that's still in the chats. Maybe due to times, we unfortunately maybe professor would like to answer it directly to the persons via emails or if it's possible.
Yes, absolutely.
Thank you very much for these presentations, and also thank you very much for accepting our invitations to do this webinar. Hopefully, this is interesting for all of us, and also this will be useful for our knowledge.
Thank you. Thank you very much. I wish you all the best.
Yeah.
Have
Thank
a
you.
wonderful. Bye-bye.
Yeah. Have a good day.
Thank you. Thank you so much.